Okay, let me start that over. So we have Andrew Fix here today with us. He's assistant professor from Maseeh Department of Civil, Architectural, and Environmental Engineering here at the University of Texas. The title of his talk today is Moisture Matters, Leveraging Water Vapor Selective Membranes in the Built Environment. So a little bit of background on Andrew. His research interests broadly include energy efficient air conditioning and atmospheric water harvesting technologies. Specifically, his research group blends material science, classical thermodynamics, analytical modeling, and prototype development and demonstration to create next generation thermal technologies that address grand challenges at the intersection of energy and water for the built environment. His bachelor's degree in mechanical engineering from University of Tulsa, PhD in mechanical from Purdue University, and he was a postdoctoral scholar at the Center for Environmental Energy Engineering at the University of Maryland. A little summary of his talk today. It is estimated that 10% global electricity is spent on cooling, ventilating buildings, and more than 50% carbon emissions for cooling our buildings stem from the condensation of water vapor in our air conditioning systems. Today, nearly 34 billion people experience water scarcity for at least 1 month out of the year, while energy sector takes up 10% of global water withdrawals. I used to study a lot more of the water energy nexus in my past, but not anymore. So improving the energy efficiency and water sustainability of our society are two interlinked problems, and one class of technologies can make an impact is in the intersection of this is water vapor selective membranes, or unique materials that allow gaseous water to transport but block the transport of all other gases. So we're going to hear about Dr. Fix's research in this area of water selective membranes and understand a bit more about the water energy nexus. So with that said, please welcome our own Andrew Fix. Thank you.
So I can skip over my own introduction, but maybe the one point that I'll try and make is that I hope that you see in this talk. I hope that this kind of intersection of mechanical engineering and material science kind of comes through. I'll talk a little bit about it, but a lot of research in the membrane space, especially, focuses on the material side, the material chemistries. But as a mechanical engineer, I'm a lot more interested at the system level, the mechanical systems that use these materials. And so, yeah, so hopefully that intersection comes through. I'm gonna mute this. Okay, cool. So as a high level overview of the presentation, what I'll talk about, I'll give you, the basic overview, the motivation for this type of research, identify a few unique challenges that we work around. And then we'll kind of go into two technical areas. We'll talk about membrane-based dehumidification for buildings and the work that we've done there. And then we'll do a little bit of discussion about atmospheric water harvesting. And that won't focus so much on membranes. It will include membranes, but we'll talk about some other technologies as well. And then just kind of wrap up with some future perspectives in this research area. So who's heard of the food water energy nexus by a show of hands? Okay, yeah, a good number, right? So ultimately, one way or another, a lot of my research stems from this idea that food, energy, and water are interlinked. Especially water and energy gets talked a lot about, the water energy nexus, but food comes into play as well. So globally, food agriculture takes up around 7% of fresh water use, and at the same time, agriculture, right, using pesticides, things like that. Those chemicals can leach off and they end up in the water, right? And that puts the burden on water purification facilities, right? So that's the interplay. Well, that's some of the interplay between food and water, right? Food and water are connected. Food and energy, it's a little bit more of a little bit more nuanced, right? But if you want to think of it this way, right? Growing food takes up a lot of energy, and if we're going to, in the future, maybe move to more and more PV, right? Both of those things require a lot of land. So there's that competing interest, but also you have the fact that food waste can be used as biofuel, and it takes a lot of energy to produce, process, and transport food. Food and energy are inherently linked to one another, and also at the end of the day, right, food is energy for humans, right, for human things. And then lastly, where we'll really talk more today is this connection between water and energy, right? So 10% of global fresh water is used for energy production around the world. And 4% of global electricity is spent on water, just by the water sector generally, right? So processing, transportation, purification, right? So all these things are interlinked, and there's some other specializations within the water energy, which is really where we find the usefulness of these membranes that we work on. And so what you're going to see is that essentially all of the research that I'm going to show and usually interested in has to do with water that is in the air. Whether that's because we're trying to keep buildings comfortable, right, keep buildings dry, or whether we're trying to generate usable water from the atmosphere. Most of my research is primarily concerned with air, so humidity and air, as opposed to traditional water resources. So focusing in a little bit more then on some specific problems, buildings consume around 40% of all primary energy in the United States, and about 10% of global electricity is spent just on cooling and ventilating buildings. So this is a really nice plot that comes from NREL. Though I don't know who follows the news, but I guess NREL is now the National Lab of the Rockies. So it comes from the National Lab of the Rockies. And it's a breakdown of the carbon emissions associated with air conditioning in buildings. So see, maybe I'll use the pointer here so that people can see online. So embodied carbon rate, that's your emissions associated with manufacturing and installing air conditioners. Refrigerants, this is something that it's not really I guess, talked about so much nowadays, but even nowadays, lots and lots of refrigerant leaks out of our air conditioners. You may know this if you're a homeowner or a car owner, right? You have to get your system recharged with refrigerant every so often, just leaking into the atmosphere. And so those are two important sources. But if we just look at these two sources up here, the temperature load and the humidity load, you see that humidity load is about 31% of the total global emissions associated with air conditioning, whereas temperature load is only about 27%. And so I think that's a really interesting finding because if you're not somebody who thinks about air conditioning every day, you might just think, well, air conditioners are there to cool the building. That's their job. And dehumidification, like maybe that's happening on the side. But as it turns out, at least on a global average, we're spending just as much, if not more, energy, thus indirect emissions, on dehumidifying buildings. So moisture in air is a big challenge for buildings, big energy challenge for buildings. On the water usage side, 4 billion people experience water scarcity for at least 1 month out of the year, and the energy sector accounts for around 10% of water withdrawals. This is just a map. It might be slightly outdated now, but it's just a map of water withdrawals by the energy sector in the US. And I think it's interesting, right? Some of the areas where you see the darkest regions, some of the most greatest values of water withdrawals are also the areas that might not have as much water resources available. I'm looking in the southwest here, right? So all this idea of water vapor in the air is causing major inefficiencies in buildings, but it's also this kind of ubiquitous resource that can be found anywhere on Earth, ultimately motivates kind of the application for these membranes that I'm going to talk about today. So the two, I guess, specific problems that I want to focus in on is that managing humidity in buildings is a major source of energy usage. And so we need more efficient dehumidification technologies. And water stress is a growing issue affecting populations around the globe. And so many of the technologies that we're developing for more efficient buildings and HVAC systems can also be leveraged to harvest water from the atmosphere. So let's talk about specifically dehumidification. So how we generally dehumidify, if you're not somebody who spent time in the HVAC world, how your typical building dehumidifies itself is you take air, whether it's air from the building that you're just recirculating, or whether it's fresh outdoor air, you take that air and you pass it through some sort of heat exchanger that's carrying a really cold fluid. It could be chilled water, it could be refrigerant, and you cool that air down until it reaches 100% relative humidity. And once you reach that point, you continue cooling the air down, and water has to then condense out of the air. And that's part of the reason why we have such low temperatures when we supply air, right? Air comes into our buildings and you feel really chilly if you're underneath a vent. Part of that is because we need really low temperatures to dry that air out enough in order to maintain healthy conditions. So anyways, the main point being here that your typical air conditioning system just condenses water, takes it from vapor, turns it into liquid, and then drains that liquid somewhere else. So consider a scenario. This is a scenario where maybe we're going to cool some fresh outdoor air for a building. maybe it's 30 degrees Celsius and 65% relative humidity, and we're going to cool it down to 10 degrees Celsius and 90% relative humidity. So 10 degrees Celsius, it's a little bit on the cold side. Usually we supply air to buildings around 13 Celsius or 55 Fahrenheit. But just to keep it simple, right? Imagine we're going to cool down to 10 degrees Celsius. The heat transfer to take it from 30 degrees and 65% relative humidity to 10 degrees and 90% relative humidity, 20 kilojoules per kilogram of heat transfer is just there to reduce the temperature. So that's your 30 degrees Celsius to 10 degrees Celsius. But 25 kilojoules per kilogram is spent turning the water in that air from vapor to liquid. So you can see right in this hypothetical scenario, condensation constitutes a large portion of that energy use. In this case, it's more than half. Now, we're also treating outdoor air, and outdoor air is hotter and more humid than indoor air. But you see the point. This little bit of condensation that is produced has a big energy implication associated. We don't actually need that water to be liquid, right? That's just convenient to turn the water into liquid. But all we really need is to get that water vapor out of the air, one way or another, get it out of the air before we send it into the building. So we are used to turning it into liquid, but what if we can do something else? And that's where water vapor selective membranes come in. So a vapor selective membrane is just usually a polymer, but it can be other materials as well. So a polymeric material that allows water vapor to transport through it, but blocks the transport of other molecules like oxygen and nitrogen. You combine it with some sort of, maybe in this case, a vacuum pump, where we create a low water vapor partial pressure or vacuum pressure on the bottom side of the membrane. Then as the warm humid air flows over top of the membrane, the difference in water vapor partial pressure will draw the water molecules out, but will block the transport of most other molecules. It will still let some of the air through, but the proportions are pretty big in terms of a lot more water vapor gets through compared to how much air molecules get through. We'll talk a little bit about why that is, but just at a high level, the pros of this type of technology would be that we don't need any sort of thermal regeneration. So you may have seen like the little desiccant packets that come in certain like pre-prepared food, rice, for example, right? Desiccants are an absorbent, and some desiccants, right, can be reused, but you usually have to put a bunch of heat into that desiccant to force the water back out if you want to reuse it. So that's another energy penalty. So we don't have that with membranes. There's no thermal regeneration process. We're avoiding condensation, which is a big energy penalty in conventional dehumidification. And overall, there's a lot of research that suggests that there's very high potential efficiency of this technology, but ultimately it's a much less mature technology than desiccants and then your typical condensation-based dehumidification. And as I'm going to kind of highlight, it requires good system design to really achieve high energy efficiency. As it turns out, right, this really basic representation that I show here, where we're just using a vacuum pump to suck the water across the membrane and then dump that water back out to the atmosphere, not an efficient system design. This is where the mechanical side of my research comes in, really thinking about mechanical system design and process design. So we'll talk a little bit about that. But I do want to also try and bridge the gap a little bit between material science. So what do these materials look like? What are their properties? Help at least provide some baseline understanding when we look at the system level performance of these types of air conditioning systems. So these are some membranes that I made a few years ago. And it's PBAX 1657. That's a commercial polymer combined with graphene oxide and coated onto a PVDF substrate. So what we see here, right, this top image is just a scanning electron microscopy image of the basic PVDF membrane. It's just something you can buy off the shelf. It's very, very porous. And then what you see in this bottom is a side view of the membrane. So we basically dipped the membrane in liquid nitrogen, snapped it in half, and then took a cross-section image of this membrane. And so you can see the really, really porous PVDF substrate down here, right, in this area. But then you see this really thin, dense region. I say dense because it doesn't look porous and open like the material below. And so that we call that the dense layer. We call these dense polymers. And that is the PVAX and graphene oxide solution that was coated on top of this porous core. So the PVDF is just there to provide structure to this really thin, dense PVAX and graphene oxide layer. And that PVAX graphene oxide layer enables what we call the solution diffusion process. So it's the way that water vapor moves through that dense layer. Again, it doesn't look like it's got any holes in it. It looks like it's just a dense polymer, no pores. There's debate actually in the literature as to whether or not there are pores, but at least to the eye, it doesn't look like there's pores, at least not at the same scale as the support structure. And so what happens then is water vapor absorbs onto the surface, diffuses through the polymer chain, and then desorbs on the opposite side of the membrane. And this is only possible with certain materials. So in this case, PVAX is a very hygroscopic polymer, has a strong affinity to interact with water vapor molecules. And so that process, that solution diffusion process, why water gets through, but air doesn't get through, because there's not these big pores for air to leak through. And air and nitrogen aren't going to kind of have this affinity with the material that water vapor does. So that's the general transport process. And this is just kind of a highlight, at least of the material properties that we measure. Now, these values won't necessarily mean anything to you. Take my word for it for a moment. The water vapor permeance here, we had about 2,500 GPU, gas permeance units. I would say that's pretty good. It's not at the top end, certainly not at the low end. It's somewhere in the middle of the pack. And we had a selectivity here around 1,000. So selectivity describes the ratio of water vapor permeance to air permeance, or in this case, nitrogen permeance. So in this case, the water vapor permeance was 1,000 times greater than the air permeance. So it's way more likely to let water vapor molecules through than it is to let air molecules through. But even that number, 1,000, is not really towards the top of the pack. It's somewhere in the middle of kind of the current literature. Why am I showing these results, though, is this membrane is really easy to make. So if you're somebody like me or the people that work in my group who are a little bit more systems oriented, it's a really easy membrane to make, and it's got pretty good properties for how easy it is to make. It's got pretty solid properties. But I'll show you just a review here of other membranes. So this is back in 2019, and they looked at a bunch of different dehumidification membranes, and they're plotting on the y-axis the selectivity, so that's the ratio, right, of water permeance to air permeance. And on the x-axis, they're showing the water vapor permeability. So again, these are not my values, right, but this is somebody else that had made a PVAX and graphene oxide membrane, and it showed up right around here, right? So it's in the middle of the pack, I would say, but towards the top end, right? Ideally, we want to maximize both permeability and selectivity. So we want to be in this top right corner. So this PVAX is kind of somewhere in the middle, but a little bit more skewed towards the higher performing end. But you can see that there's a range of other materials that have been found to outperform even PVAX. And so this Nexar membrane that are shown in blue, those are also pretty good and pretty easy to make. And those are membranes that we're starting to make in my group as well now. But anyways, this is just to give you a reference point of kind of where we're at. These PVAX membranes are pretty good, and they're really easy to make. So they're great if you just want to make some membranes and then develop new systems to use these membranes. Okay, so we've got the materials. Now, we essentially need some sort of efficient system or some sort of cycle that can use these membranes to efficiently remove humidity from buildings. And I want to draw inspiration from refrigeration cycles. Ultimately, a lot of my background goes back to classical thermodynamics, right? The refrigeration cycle. So if we think about the refrigeration cycle, which is how we cool most buildings one way or another, you basically have a device that can hold heat from indoor space and pump that heat somewhere else. We pump it outdoors. We take low temperature heat, we put it into our heat pump system, and then it turns it into high temperature heat, and we reject it somewhere else. We reject it outside the building. And this is manifested in what we call the vapor compression cycle. It's just a refrigeration cycle that has two heat exchangers, a compressor and an expansion valve, and we effectively pump heat from one room, to the outdoors by recirculating this refrigerant flow between these two heat exchangers. To put it really simply, and so we want to develop some sort of system or some sort of cycle that does the same, but instead of moving heat out of buildings, we want to move humidity out of buildings. So we want it to be analogous, but we're replacing heat with humidity, with water molecules. And that brings us to this concept of the dual molecular humidity problem. So this is a concept that's been around for a while, that ultimately we've expanded on and brought it closer to the real world and away from just conceptual ideas. But I'll show you the conceptual idea first, and then talk about how we actually implement it. So the idea behind this dual module humidity pump, again, I want it to be as clear as possible that it's essentially analogous to a heat pump. So a heat pump is pumping heat from, or your air conditioner cycle is pumping heat from inside the building to outside. We're going to do the same now, but with water vapor instead of heat. So we have a membrane module. Humid air flows over this membrane. We maintain a vacuum pressure on the bottom side of that membrane. The difference in water vapor partial pressure draws the water out of the air, and now we have to do something with it. And so what we do is we implement a central water vapor compressor, but instead of compressing this water vapor and just sending it back up to atmosphere, right? So this is about, I'm just using hypothetical numbers here, but I've listed it as 1 atmosphere, or about 1 kilopascal, 0.01 atmosphere, sorry. So about 1 kilopascal. And atmosphere is about 100 kilopascals. So we're going to try and pressurize that water vapor from 1 kilopascal to 100 kilopascals. It's a pressure ratio of 100, really, really big pressure ratio. Your vacuum pump or your compressor is going to be really inefficient. It's going to consume a lot of energy. So you're just not going to get a very efficient separation process. It's going to consume a lot of energy. So what we do instead is we send it to a second membrane module. So in the same way that your air conditioner has 2 heat exchangers, it has a heat exchanger inside that's cooling the building, it has a heat exchanger outside that is rejecting heat. Now we have 2 membrane mass exchangers. One of them is dehumidifying, pulling water vapor out of the indoor air, and then another membrane module where we are dumping that water vapor somewhere else. We could be dumping it to the outside, we could be dumping it to some sort of exhaust air, doesn't really matter. And the major point here is that as long as the pressure here at state 6 is greater than the water vapor partial pressure of the air flowing on the opposite side of the membrane, what drives mass transport in this case is the difference in water vapor partial pressure, not the total pressure. So we can do really small compression ratios. So maybe P6 divided by P5 might be 5 or 10, right? So much, much smaller increase in pressure. So we're going to get a much lower energy consumption to cause that compression. And then we're just going to push that water vapor across the selected membrane, and that's going to carry the water vapor away instead of just compressing the mixture all the way back up to atmosphere. So the key point here, right, is that vapor transport is driven by vapor partial pressure difference, not the total pressure difference. So we don't need to compress that water vapor mixture at state 6 all the way back up to atmospheric pressure. And then again, right, what we're essentially doing here is we've got a humidity pump. We're pumping humidity from one airflow to another. One of them's lower pressure, one of them's higher pressure. And so it's relatively analogous to the heat pump. And so the benefits here is that we've got a much smaller compression ratio for that gas than if we were just going to use a vacuum pump and compress all of that water vapor back up to atmosphere. So reduced compression ratio, which means less power consumption, and there's no condensation process, right? So we're hypothetically avoiding any sort of energy penalties associated with trying to condense the water. And so this gives it, really high potential efficiency. There's a wide range of publications that look at this kind of hypothetical system and show that, at least from a thermodynamic perspective, it's got a lot of potential. But the problem, until quite recently, is that there have been a handful of publications that looked at this concept and said, wow, look at this. Like it's got such great COPs. It's got really, really good energy efficiency, but nobody had built it yet. And so I guess maybe 2 years ago now, we published kind of the first experimental demonstration of this. And we ran into some issues when we were actually trying to build this new air conditioning cycle. So this is what I showed you previously. Essentially, it's a little bit different. Right now, at least, the only difference about this compared to what I just showed you is that I'm also showing that these membranes aren't perfect, and so they are going to allow a little bit of air to leak in through the membrane as well as water vapor. And you have to compress that, right? If air leaks in, then that is with the water vapor, and you have to compress that too. And you have to spend the energy to compress that air as well. You have to compress the whole gas mixture. But what we found when we actually built a prototype that kind of looked like this was that air, since these membranes are pretty impermeable to air, once you start to get air leaking into the vacuum portion of the system, it builds up. And it builds up in this bottom vacuum channel shown here. And as soon as that air pressure starts to build up, totally inhibits mass transfer. So you don't see any water vapor successfully being pushed across this membrane because you're immediately inhibiting that mass transfer by building up other molecules, other non-permeable molecules like air. And now the water has to try and diffuse its way through the air layer to get to the membrane. So it totally inhibited the performance. It just didn't work like we thought it would. And so at least to make the experiment work, to demonstrate conceptually that this system is possible, we added this vacuum pump in series. So now what happens, right, is we flow air over this membrane, we create a vacuum pressure to pull water vapor out, a little bit of air gets through as well. So now we've got mostly water vapor, a little bit of air. We compress it slightly, maybe a compression ratio of 5 or something like that. We reject all, if we can, but at least most of the water vapor across the membrane, so that leaving this vacuum channel, it's mostly just air, the stuff that we can't actually push across a membrane. We try and minimize how much air is being pulled out here, because compressing that air from this point back up to the atmosphere is going to consume a lot of energy. That's a big pressure ratio. That's going to be relatively inefficient. So if we can minimize how much gas actually gets sent to that vacuum pump, we can improve our efficiency. And so by making this modification, we were actually able to demonstrate that this concept does work. I think one of the more interesting things, right, is I think this idea that the pressure in this channel can be vacuum, and this can be positive pressure, but we would still see water vapor molecules moving in the opposite direction of the total pressure difference. It's kind of confusing, and we were able to show with experiments like it does work. Even if the system has deviated kind of from the ideal cycle design. And so this is well, I'll just kind of run through a couple of experimental performance demonstration results. So here we're looking at dehumidification fraction versus the air flow rate. I think it's a relatively self-explanatory result, which is that with this prototype we built, we were able to remove up to about 45% of the airflow, or 45% of the humidity in the airflow, and that's pretty good. That's about what we would need for an air conditioning cycle. And ultimately, though, right, 5 to 20 liters per minute is a very small flow rate of air. In a real building, we'd have way, way more than that. But the simple solution to that is you just need more membrane area for more airflow. You need more dehumidification. You build a bigger system. We were just building a little benchtop prototype, but it's at least feasible. But I think maybe a more interesting experimental result, again, this is something that never came up in any of the theoretical literature that were suggesting that this cycle design would be really, really good, was this idea. So think back, right? We've got these two modules. We've got one where we're removing humidity from air, and we've got another module where we're trying to dump that humidity into some other exhaust airflow. And so ideally, whatever rate of humidity we're moving up here, we want that mass flow rate of water vapor to be equal to the mass flow rate of water vapor that we're actually rejecting in our other module. And that's exactly what the y-axis value shows here. So I call it the vapor balance ratio, and it's just the rate of water vapor rejection divided by the rate of water vapor that was removed by that top membrane module. And we want that to be 1. We want those two things to be balanced out so that we have a steady state system. But what we found, at least in our experimental prototype, was we were maxing out our system more around 60 to 65%, which meant that that other 35 or 40% of water vapor that is unaccounted for is just being removed by the vacuum pump, just being compressed back up to the atmospheric pressure. And that's, again, I want to really stress, if we're just compressing gas mixtures all the way back up to atmospheric pressures from vacuum, that's inefficient. That takes a lot of energy. So this is interesting, right? And this is just kind of a preliminary prototype demonstration, but it's a major limitation, right? And so then the next question is, okay, so we're not quite achieving the ideal performance, and there's no real literature that has ever considered that this might not, this ideal performance might not be what you actually see. So we built a thermodynamic model of the cycle, and basically used this vapor balance ratio as an input to the model to say, okay, as we vary this variable, how does that affect our overall energy efficiency? And that's what I'm showing here. So the y-axis is the latent coefficient of performance. For those of you that have taken thermodynamics, right, coefficient of performance is usually just heat transfer divided by work for like a vapor compression cycle. For the purpose of this presentation, just take that y-axis as an efficiency metric. It's just some sort of measure of the energy efficiency of the steamidification process. And your typical air conditioner has a COP of about 4. It totally depends on the operating conditions, but ranges from 3 to 5, 3 to 6. So let's call it 4. That's just kind of an average value. And with that as our kind of average value that we want to try and beat, then you can see that we need this vapor balance ratio to be greater than 90%. Right? We need to hit around this benchmark in order to reach that competitive efficiency, where this system is just as competitive as a standard refrigeration cycle. And if we can push it to the ideal case of 1, then we far outnumber, right? We maybe even double the efficiency. But we get really exponential growth as we push past this kind of 90% vapor rejection ratio benchmark. And that's ultimately a cycle design problem. We need better cycle designs, we need better component designs in order to really achieve this. The other half of this is I want to talk about how the membrane properties affect system performance. So this is a plot again of the COP. It's the same type of COP. The y-axis is labeled differently, but it means the same thing. And on the x-axis, we have selectivity. And note that it's times 10 to the third over here. So 10 is actually 10,000. And what you would imagine, right, is if you have a really poorly selected membrane, it lets lots of air through. It's really not good at blocking air molecules. Well, then we've got a lot of air, we've got a lot of water that's getting through the membrane, and we have to compress all of that gas. And all we really want the system to do is pull the water and compress the water. Air is just a byproduct, and if we have to compress the air, that's a complete waste of our energy. And so you would expect that lower selectivity means that more air is leaking into the system, which means that more gas is being sent to the compressor, which means more energy is being spent on compression processes. And that's exactly what you see. As selectivity increases, we let less air leak into the system, our efficiency increases. Again, if we're shooting for this kind of competitive COP of 4, then you can see I would say around selectivity of in the range of kind of 10 to 100,000 is going to be ideal, right? Once we push past that, we're going to keep getting efficiency benchmarks. And so if you think back, right, with that in mind, I showed you some membranes that we made, and the selectivity of that for that particular membrane was about 1,000. We made a version of them later on that was more in the 50,000 range. And so I guess the main takeaway here is that membrane selectivity makes a big difference as well. So it's not just the challenges aren't just around system design. We also need good materials, good robust materials that last a long time. And there's a handful of membranes that have already far exceeded this benchmark of 100,000. Now the question is making them easy and scalable to make at a large scale. You could actually implement them in these systems. I also want to provide a little bit of kind of context, right? So what we talked about now is we've talked about some experimental demonstrations. We've talked about a little bit more nuance of how material properties affect system performance. But let's take a look at the big picture. So we basically put together some models of conventional air conditioning systems and membrane-based air conditioning systems in Engineering Equation Solver. And then we combined this with building simulations in Energy Plus and used the outputs of the building energy simulations. So, the hourly profile of the building loads, the temperature, ventilation rates, things like that, as inputs into our system model. So we could say, well, how does our membrane-based air conditioning system compare to other air conditioning systems? And so for kind of what I'll call a well-designed membrane-based air conditioning system, so this would be a system where we've maximized that vapor balance ratio, right? So we've got good balance between the dehumidification rate and the vapor rejection rate with good membrane selectivity based on the current state of the art. It's essentially what we're looking at here. So what can we ultimately achieve realistically with these types of systems? And I think the results are maybe somewhat obvious, right? That the highest energy savings are in these kind of southern coast regions, right? Texas, Florida, Mississippi, Alabama. Right where it's hot and humid. If there's more humidity in the air, there's more potential to save energy because this technology ultimately really targeting improving the efficiency of dehumidification. And that can have some implications for improving the efficiency of cooling as well, but we're really targeting humidity as our area to reduce energy consumption. And so on average, we saw that there's potential to save up to 15% annual cooling dehumidification energy savings in the US. This is also a really interesting result too. We looked at basically how does the building type matter as well. And you can see, right, that restaurants, in this case, far outweigh the energy savings of all the other types of buildings. And that was something that we weren't thinking about initially, but makes sense. Restaurants have pretty high density of people. They pack you in there, several at a table, right? You've got the kitchen putting off a bunch of humidity from cooking. You've got higher ventilation rates, which means you need to bring in more fresh outdoor air to maintain indoor air quality levels at a satisfactory level. So there's a lot more humidity loads in a restaurant, so a lot more potential. And I think that this is just relevant because it helps at least inform you, right? The building type matters too. So where are we going to try and implement these technologies first? Probably not your home, right? Where there's pretty low humidity levels. There's not much outdoor air that you're bringing in. We want to focus on the application areas and the environments where it's going to make the most impact. And I meant to take the slide out, so I'm going to skip it. But the main takeaway is that there's a lot of potential, but there's a lot of challenges. I'm going to cover the challenges towards the end of the presentation. Now I want to quickly switch over to talk briefly about atmospheric water harvesting before we wrap up. And so the motivation on the atmospheric water harvesting side, as we kind of make this jump to another area, is that of all the fresh water on Earth, 68% is in ice and glaciers, 30% is in the ground, and 2% is everywhere else. Rivers are about 2,100 cubic kilometers of fresh water, and at any given time, there's about 13,000 cubic kilometers of water in the atmosphere. We don't really take advantage of this, and so atmospheric water harvesting is just a class of technologies that tries to harvest this water from the air to try and provide a good opportunity for decentralized water, right? What I mean by that is your typical water infrastructure, right? You purify and produce that water somewhere centrally, pipe it out to larger community. And what we want to do with decentralized water is take smaller communities or even individual buildings and install small-scale on-site water production and purification there. So it's decentralized, as the name implies. And so most of my work in atmospheric water harvesting, previously at least, was really focused on how do we compare water harvesting technologies. There's a wide range of different water harvesting technologies that have been proposed. There's membranes, there's your typical refrigeration-based condensation water harvesting, there's sorbents. And in some of these classes of technologies, companies can make the claim that, well, it's super efficient because it just uses waste heat or it just uses solar heat. And that you don't have to pay anything for that. That's free. Which is true from an economic standpoint, but we wanted to understand, fundamentally, which of these technologies, at least from a second law thermodynamics perspective, are actually the most efficient, regardless of where that energy input is coming from, whether it's free or not. Which technologies make the best use of the energy that they are fed, essentially. And that was the question that we asked ourselves, and ultimately we derived a second law of thermodynamics framework, essentially building on Gibbs free energy concepts to develop what we call the minimum least work of atmospheric water harvesting. So it's regardless of what your technology is, just from a fundamental standpoint, if you want to take water molecules out of the air, put them into a liquid form, what is the least amount of energy per kilogram of water that you have to spend in order to do that? And then we can compare every other type of water harvesting technology against that fundamental limit as our benchmark. And just as kind of a high level review of some of the outcomes of that, right? So this is a plot that shows air temperature on the x-axis and humidity on the y-axis. And we basically, it's hard to read, but we basically mapped out in what weather conditions does each technology make the most sense. What was, I think, surprising is that just basic refrigeration-based dew harvesting, so that's forcing condensation to occur, shines from a fundamental standpoint, a wide range of conditions. In sorbents and membranes, which are a little bit more advanced forms of water harvesting technologies, find their niche really in arid climates. So, remote arid communities that don't otherwise have good sources of water would probably benefit more from these more advanced concepts of using membranes and sorbents because they can still remove humidity even when it's really, really dry in the air. Whereas your normal condensation-based water harvester is going to really struggle in those arid climates. And so we created a global map of the minimum energy requirements for water harvesting. So again, that's your benchmark that you can compare any other technology against to figure out how good is your system compared to somebody else's. And we also created a map for the average day across the entire globe, which technology is going to be best suited for that location, for that climate. Lastly, the hot topic that I think is on everyone's minds is data centers, right? Everybody seems to be talking about them nowadays, and it's not necessarily something that we've worked on in the past, but it is an area that I think is relevant to a lot of what I do, right? So in data centers, most use economizers, which are basic HVAC systems that decide, if the air inside the building is pretty hot and the air outside the building is pretty cold, why would I keep recirculating the hot indoor air and cooling that back down when I could just bring in outside air that's already cold and just bring that into the building? So there could be scenarios where the outdoor air is relatively cool compared to the inside, but maybe it's still pretty humid. We don't want to bring humidity into the building when you've got a bunch of expensive racks going. And so we could be adding, separate dehumidification technologies to economizers to increase the operable range of economizers. Most data centers use cooling towers, and cooling towers lose a bunch of water in the evaporative cooling process, and we could try and basically implement water capture technologies essentially with cooling towers to try and create kind of a closed economy, if you will, for water, right? Just keep it as much of it as we can without having to really rely on extracting water from local communities and local resources. Indirect evaporative cooling, it's a pretty low electricity form of cooling, but it also requires a lot of water. And so you could hypothetically install on-site atmospheric water generation and feed your indirect evaporative cooler with on-site generated water, so you're not impacting surrounding communities. You could use that on-site water generated to feed your cooling towers. There's a lot of opportunities to use the ever-abundant resource of humidity and air for various needs in data centers. So this is something that we're starting to think about as well, just given the kind of growing need for that, especially here in the US. So to wrap up, some of the challenges and major barriers between selective membranes and broader adoption, we need to keep improving selectivity and making these membranes really robust and easy to scale up. We need commercial membranes, right? Right now, if I want to focus on system design, system innovation, I can't do that until I make my own membranes. So I have to try and do both. And so it'd be great if we could find a way to make these commercially viable so that I can just buy them if I want to focus on systems. If somebody else wants to focus on systems, they don't have to become a membrane material expert as well. Long-term performance is a pretty big question mark. No one's really studied these to see how they will last over a long time. That will severely impact the economics of it. Water vapor compression technologies are kind of a niche. They don't have a wide range in other applications. So making sure that we have well-designed water vapor compression technologies. And ultimately, we need more experimental demonstrations of the efficient systems, right? We've got lots and lots of materials work, very little experimental demonstration of actual HVAC systems that can use these materials. So we need more of that. So we're addressing a lot of these in our group. We're working on both modeling and demonstration of new cycle designs. We're developing new membranes and working with membrane industry. We're looking at how mechanical stress affects the long-term performance of membranes. If they're exposed to a vacuum pressure for hopefully years and years on end, it's going to stress the membranes out, and we don't really know how that's going to affect their ability to separate water vapor molecules and block other gas molecules. And ultimately, we need techno-economic benchmarks. We need to know how much these things need to cost, how much energy savings they need to provide in order to really make economic sense. And that's just not something that's been looked at yet. So in conclusion, membrane-based air dehumidification provide substantial annual cooling savings, especially in humid climates. And we need to push the membrane selectivity still. We need to get membrane selectivity to be reliably above 100,000 to really approach the maximum possible energy savings. And while there's a number of membranes that have pushed well beyond this limit, the vast majority find themselves still kind of around or below that threshold. And ultimately, water harvesting can also provide a really great source of decentralized water around the globe for a range of existing societal challenges. And so ultimately, the main takeaway, if you take one thing away, vapor-selective membranes have great potential in a wide range of applications. And there's a lot of exciting innovations going on in the space. So hopefully you'll keep an eye out on these types of research, and hopefully sometime in your lifetime, we'll be selling membrane-based HVAC systems globally. So with that, I will take questions. Thank you very much for your time.
Okay, thank you. Questions in the room first? Right, well, I'll go with one on the online here. And let's see if I can type strange and see if I can read it correctly. Could a massive deployment of atmospheric water harvesting technologies create a greater imbalance with atmospheric moisture, improve climate, natural ecosystem disruption? I guess that's kind of a larger, even larger systems question than maybe you think about is how do people think about, I don't know, pros and cons.
Yeah.
Atmospheric water harvesting and regional climate, or
It's
localized.
Yeah, it's a super interesting question. I've been asked that question a lot, and So like Arizona State has like an sort of water harvesting consortium. They wrote like a news article where they basically, it wasn't a full research study, but their conclusion was basically that it won't have environmental impacts. But I think it's a really hard question to answer because it totally depends on the scale. So the way that I think about it, like right now, is like, for example, this campus has tons of cooling towers on it, and cooling towers put off humidity. You essentially spray water or some air. A lot of that water evaporates to provide a cooling effect, and that water gets carried away. I don't know that we've ever talked about, universities, for example, like being really humid because cooling towers are putting off a bunch of humidity from the cooling towers. So that's just kind of an anecdotal answer, but it's a really important question. I have an undergraduate who's kind of exploring this idea a little bit. Basically, he's been looking at if we extracted all of the water vapor that is in the air above Austin, how much water would that be? And how does that compare to how much water we actually use in a day? Preliminary findings is that there's so much water in the air that it would be really hard to drastically change it.
Anecdotally, I can say walking by the cooling towers in the middle of the summer here doesn't feel great.
Yeah,
And
sure.
they
Up
say
close.
this.
Up close. Yeah.
I can feel it if I'm close enough.
Yeah.
Hey, I was wondering, have you looked at basically how this economically compares to just sort of classic condensate recovery that you would do with a typical air handling system? Like
You
where you
mean,
basically recover the condensate and what affects the cooling towers?
yeah. So how does what compare economically?
Basically, how does that shift the economics of what you're doing, I guess?
Yeah, I haven't particularly considered that, but I know UT has like a lot of condensate recovery. And so I've been trying to like learn more about what they're doing because that's not that common. A lot of buildings just dump it into the sewage. So
Yeah,
um,
the city of Boston, I think now requires it. So.
okay, cool. Yeah. So but I have another undergraduate who's kind of looking into, how much water are we really producing in different types of buildings from air conditioner condensate. So yeah, I think that's another untapped area. We have a project with the EPA that it's been taking a long time, but we studied kind of what we found in air conditioner condensate and where that might be coming from too. And so hopefully that'll get published soon. That's another interesting area of water resource.
Yeah, so it's sort of a question of who's interested in this. I guess you kind of mentioned, I guess membrane companies are interested in this because they need to make the membranes, and as you're implying, we sort of first need the membranes before you can make an effective
Right.
cooling system design, but who else is kind of interested in this so far? Are HVAC type cooling companies interested?
Yeah.
Are they waiting on the sideline for a while?
Yeah, so actually, there's been more interest from the HVAC industry. So at Purdue, which is where a lot of this research was conducted, it was funded for 4 of my 4.5 years there by HVAC companies specifically. So your Trains, Carriers, Emerson. So they're really interested because they're always the HVAC industry is constantly under pressure to get cleaner and cleaner, right? We keep changing the types of refrigerants that we're using. So yeah, the HVAC industry is pretty supportive, and actually it's been more challenging finding membrane companies that are particularly interested. So we're fortunate that recently this year we found a company that's headquartered in Houston. They're like already really interested in this. So hoping to push that along because the HVAC companies can help us maybe with manufacturing down the road, but we need good, reliable membranes first. HVAC companies don't know anything about making membranes right now. So
Here's your maybe classic question these days. We're going to throw AI question, which is maybe I'll phrase it as a design question. Is there any plan to incorporate artificial intelligence into your dual module humidity pump design, which is maybe a way to say how much have you thought about, or has anybody asked about? Yeah, using AI to solve for some optimization problem versus you've got your thermodynamic approach, which I love your graph and trying to figure out the minimum energy requirements based upon design. So are we still at the basic thermo level here and some hardcore engineering?
Yeah, in my opinion, right. So I've seen some papers that have taken, basically thermodynamic models of similar concepts, right, that haven't necessarily been proven experimentally, but similar concepts, and do some sort of optimization. But at least for my own research methodology, like I want to know that everything works, that we've demonstrated it before we really spend too much time trying to do AI optimization. I think maybe where it comes into play is perhaps less with the membrane module and system itself, but building controls is a whole other area of research. Right, trying to predict thermal loads, trying to predict, how much cooling am I going to need today, how much dehumidification am I going to need today. I think that sort of thing makes a lot of sense in the near term in terms of AI integration with this or with any HVAC technologies, is using AI to kind of predict and optimize overall building cooling energy use.
All right. Anything else? I think, I'm trying to make sure I understood your sort of thermodynamic minimum chart well enough, where you kind of say, so you're studying this membrane approach.
Yeah.
And it was sort of in a very small level of, so the membranes are down there at the bottom.
Yeah.
So in some sense, very hot, but not that humid areas, and for the most of, well, you have your chart across the United States for looking at this energy savings.
Yep.
Potential by using membranes. So we say, most of the United States is like this is not in the membrane territory, or at least the savings.
Oh, this is a totally different, this is a totally different thing, right? So, what we're saying here is basically, for this quote unquote well-designed system, it'll save energy anywhere, but in the Northwest, for example, it's going to be maybe 2 to 5% or something like that, right? It's going to be relatively small. Whereas in the southern tip of Florida, right, we can pretty reliably bet that there's a lot of potential for energy savings there. So,
Okay. Anything else in the room? This one may be. I'm not sure I understand it. Maybe you'll understand. So I'll just say it. So I think it's referring to water vapor. So why is vapor absorption, not water vapor, better than absorption of nitrogen or other molecules in the air that water vapor separates from the air? I don't know. I don't know.
I mean, they're
understand that. Or,
I think they're trying to understand better, like why did water molecules get through? This gets into a bit more materials chemistry that is truly my expertise, but water is a unique molecule in the sense that it's polar H bond, right? Is a really unique, interaction that governs a lot of interesting phenomena in our universe. And so these polymers have particular functional groups that are particularly prone to interacting with and forming H bonds, essentially. Whereas nitrogen is not going to have that. Oxygen is not going to have that. So it goes back to these functional groups that want to interact with polar water molecules, essentially.
okay.
But beyond that is kind of getting into a lot of nuance details.
So this may be too much nuance for your knowledge on membrane material science. You said earlier, and I wrote down a note earlier, you mentioned with particular membrane coating we were working with is PVAX, graphene oxide, and you said there's a debate of whether it's actually porous or not.
Yeah.
So this just gets into there's more than one way to move a molecule through material.
There's a really interesting debate going on between a professor here and a professor at Rice. And they both have competing theories. One says that this method that I talked about is how it works. And that's what I've read mostly. We have another professor at Rice, though, who is very famous, like 200,000 citations type of professor, who says there are these tiny little nanopores that do let little bits of clusters of water molecules move through, as opposed to really big pores where you've got bulk flow moving through the pores. And so it's kind of been interesting from my perspective because they'll both publish papers. So the title is kind of my theory is right, that other theory is not right. And it's kind of been this back and forth, and they both make really compelling arguments. And so, and they're both veterans. So I just throw that out there as it's an ongoing debate, and it's fun to keep a tab on and see where that goes.
Yeah, strange to sometimes see this disagreement on, in principle, things we could measure by engineering, but some things are hard to
It's
see
really,
what's
really hard
actually
to
going on
yeah.
still. So that's interesting. So at some level, we just have a device that works and we understand it.
And that's other
make a
people's
trade-off,
viewpoint too, right? It's does it really matter what the model is? Both models that describe it give you the same essential result. It's just the argument is which one is physically accurate.
Yes.
So yeah, it's an interesting debate.
Okay, that's our debate for academic candidates. That's what we're doing.
Yeah.
Okay, well, let's thank our speaker again. So thank you, Andrew. Fix.